So there were three topics this week. There was the direction fields, sketching the direction fields and what they mean, how you use them to sketch solutions. And then there was solving separable equations, first order separable and first order linear. So where are you up to with that?
I've kind of been able to kind of go through all of them, different stages. I was just looking at question 1 on the workshop, and I think I got so far and then missed something else. So actually, I don't think I've got the right answer, but yeah, I've managed to have a go. It took me a little bit to get my head around direction fields for some reason.
Yes.
Yeah.
Just on how to draw the graph and what the actual procedure was, because sometimes the books, it's kind of like try to make sense of the book, do some practice, and then go back to the book because you'll understand it a little bit better.
Yeah.
Go back, kind of thing.
They are a bit, I mean, they're a bit hard to do by hand, but easier on a computer, but it's also quite instructive to do it by hand because then you actually have to think about every little bit.
Yeah. So it was that bit that was like, but I'm gonna have to remember how to do graphs again and remember my tangents and stuff like that.
Yeah.
It's sort of got there. It's sort of got there.
Yeah. What threw me off slightly with the solution curve with one of the questions was plotting y and then the y function rather than it going across x, which I think was one of the first questions. You had to plot autonomous solutions, a solution curve.
Do you remember where that question came from? Was that on the practice problems?
I think it was practice problems. Yeah. I'll have a look.
Was it the first one on the practice sheet with where, yeah, because you've got where the function, you plotted the y against the function of y. Like,
yeah, because and the function was something like y minus y cubed, I think. Yeah. And it was, you found the critical points, which was 0,
That's
3.
right. Yes.
Yeah.
Yeah, that is a good point. Yeah, so in the general case, you have dy dx equals the function of x and y.
Yeah.
So you wouldn't be easy to graph the right hand side because it depends on 2 variables.
Yeah.
Yeah, that's right. So did you sort that out?
I think, yeah, I think I've got it now. I had to remember that plotting, what was it? Y minus y cubed was the was still a derivative. So it was
so what you need to do
rather than the solution.
Yeah, so you need to go away and sort of make a little side graph of y minus y cubes.
Yeah.
Sketch the graph of a polynomial. And then, yeah, to interpret it, you tell yourself, well, that's just telling me the value of dy dx.
Yeah.
In particular, is it increasing or decreasing? Yeah.
Yeah, once I remembered that it wasn't actually a solution, it was just telling me how the solution was changing, then it made more sense.
That's what taught me a bit. And then once I clicked, actually, that's part of the method to indicate where you're meant to go.
Yeah.
And so actually that's the first thing you do, just to kind of like direct you towards, right, this is where it's going to be positive, this is where it's going to be negative when you actually draw the critical points graph and x kind of thing or whatever.
Yeah.
Or someone else. Hi, Danny.
Sorry, I need to change my name. Apologies.
Not Danny. Who is it?
Sorry for being late. It's Abby.
Hi, Abby. No problem. Well, I'm wondering what I've got to do about a problem that I've got, which is that I don't have my magic pen to write on the screen, which really makes drawing maths equations a lot harder.
Yeah.
It was there yesterday, and it wasn't there today. So
Must have been a kid or a dog.
yeah. There's too many laptops and things flying around. So we could look at one of those direction field ones. What would be the best way to? Maybe if I can still draw on the screen with my finger, so it's just not as accurate. But, and on this tool here, can I type? Oh, yeah, I can too. So let's do dy dx. I thought that was a start of a sentence. So I was thinking we could do x squared minus y squared. And we want to draw the direction field and sketch solutions. Are there any steady states? And I've chosen one with a slightly more complicated right-hand side, x squared minus y squared. Because the ones I did in the videos were chosen to be very simple just to get started. So x squared minus y squared is more complicated. So can I draw on? Why doesn't it want to do that? Yes, it does like that. This is going to be pretty messy. Well, how would you start? What would be a possible point to start? What's a point where we know where we could draw a direction stick?
Well, that would be the critical points where equals 0 would be if we work that out, wouldn't that?
Yeah, that's a good idea. So if the right-hand side is 0, that means the slope of the solution has to be 0 at that point. Yeah. So we could go back and work out. Can I type in here? No. What do you type? Do I just start typing? Oh yeah. Go up here. No, we don't. Go here. If you set the right-hand side equal to 0 and solve, you'll get x squared equals y squared. And there'll actually be two solutions, because when you take the square root of both sides, it could be a plus or minus square root. So you get y equals x and y equals minus x as the solutions. Or you could have factored that and say that x squared minus y squared minus y, x plus y. And then the two solutions would be y equals x and y equals minus x. So everywhere, so those are both straight lines, the line y equals x and the line y equals minus x. So everywhere on those lines, I'm just going to do it approximately. I'm going to have a little horizontal line with one at 0, 0. How to draw. So everywhere on the line y equals x, I'll put a little horizontal stick because dy dx must be 0. And then the same thing on y equals minus x. It's supposed to be horizontal. Whoops. There we go. Okay, that's good. So that's a start. What could I do next? What are some other x and y values that I could try drawing? Some little direction sticks.
Would you choose values between the critical points and see where they are?
Yeah. Yeah, so the easiest ones, I was thinking I might try to do the x-axis and the y-axis next, just because that would be a little bit easier.
Yeah.
So what kind of, I don't know, it's actually possible for you guys to draw on the shared screen too, actually. So if we look on y equals 0, that's the x-axis. What's going to be happening then?
On the x and positive x, positive y, did you say?
No, if I look on the x-axis.
Oh, yeah.
That is where, can you see the mouse when I point around here?
Yeah. Oh, yeah.
So here's the x-axis, and that's when y is 0.
Yeah.
So if I plug in y equals 0, what do I get?
You just get that, you get the U shape, don't you? Because you get the x squared, don't you?
Yeah, you get x squared.
Yeah.
So what would be what little
So would it start off the tangent line going up slowly and get fast, like steeper and steeper?
Yeah, that's right. Let's see if I can draw it. So when x is small, that x squared is a small number, so it's still a very small slope.
Yeah.
And then it's going to get steeper and steeper, and then quite rapidly getting very steep because x squared is getting very big. Okay. It's not brilliant, but it gives you the idea. And what about when x is negative?
It just becomes positive, so it's still a positive tangent line.
Yeah, so it's the same thing over here, a small positive slope here, and then steeper and steeper and steeper positive slope out here because x squared is getting bigger and bigger.
Yeah.
That's good. And what about on the y-axis?
So because it's a negative, that would be decreasing, won't it? Whatever the y value is, it will be decreasing.
Yes. So if you substitute x equals 0, you'll get negative y squared, which is always going to be less than or equal to 0. So you get a downward slope. Steeper and steeper and steeper. A little bit down, more down, more down, more down, very steeply down. Yeah, and all the in-between places, which we haven't drawn yet, they will just fill in smoothly. So in particular, everything in that right-hand quadrant, or that right-hand piece, to the right of my X shape. So everything over here, that's where x squared is bigger than y squared, so x squared minus y is positive. So in there I'll have just intermediate slopes like that. Positive. And then in here, when up here in this top quarter, x squared minus y squared will be negative. So it's really the sign that I'm looking for. So I've really done a terrible job here. I could plead that if I had my pen with me, I'd be doing better. So we might now be able to sketch some solutions. So the thing to do here, I haven't really drawn enough sticks here, but if you start at one point, like I'll start here, and I know the tangent is horizontal, so I'll be going to the right, and then I'll be in a region where the slope has to be negative, and it has to get more and more negative, but then it has to reach the point here, has to reach the line y equals x, where the slope is 0 again, so it has to level out. Then it's in a place where the slope has to be positive, so it has to start going up again. But you notice it can't go up too much because it can't cross that line y equals x again, so it really just has to head out in that direction. So I can sketch the solution. It has to go along, down, along, and up again. I start further over to, or in fact, I can follow this solution backwards. Now the slope has to get more and more and more negative, so it has to go down very steeply. But now I'm into the region where it's getting less steep again. So it has to, come on, you can do it. Level out and go like that. So this is a very complicated nonlinear differential equation. It's not even separable, so it would be quite difficult to even solve this. But you can get a picture of what the solutions look like. You can do another one if I start and here. But I guess from too far over. Yeah, so you can, even with a really terrible picture like that, you can get a feeling for what the solutions look like. And see if I have octave up. Still. Running? What happened? No. Don't know where my octave's gone. Oh, well, we can imagine that this thing would actually work. Then we could do a big grid of like 20 by 20 grid points and draw the little direction fields everywhere. And the finer you make that grid, the easier it gets to visualize the solutions. You could then draw the solution fields very easily by hand.
On your lecture, you plugged this into, I believe you were using Octave. Is that something that we should already know how to do?
No, so on the computer work, there is this MATLAB workbook. Have you seen that? It's on the stream site.
Yeah, I watched the video.
Oh, okay, that's a good start. So then there's this workbook that you can download that goes through section by section how to do each topic of the course on the computer on MATLAB. However, there is an issue I haven't resolved yet, which is people using this free version of MATLAB or free open source version called Octave. That's what I was trying. And it doesn't have, unfortunately, oh, what? Wants to restart my device. Oh, I can't believe it. Your organization will restart your device at 4:31. Make sure you save your work before then, or restart now if you're ready. I don't want to do that, but I'll have to go going another laptop. You can't learn. You can't actually stop that when it happens. So I have got. There is this difficulty that the symbolic part, where you like type in a formula and differentiate it or integrate it symbolically in MATLAB, is a little bit harder to get working in Octave. So I asked Carlo Lang about it, and he says it is working for him in his Octave install, and it wasn't working on mine. So I haven't managed to resolve that yet.
Okay, but short answer is no, we don't. We shouldn't know how to do that already. I just didn't know if I've.
Yeah, that's right. I'll send out more notices about this once I resolve this issue. So
Okay,
oh, here it is. This will be this the computer part where you do some computer work. This will be assessed in the assignments and not in the tests. Yeah.
Cool.
So you can see this Octave screen now.
No, I still see your OneNote.
Oh, okay. So
there's going to be some. So I don't need to do Gamba Octave MATLAB application for the test, right?
yes, it will be assessed on the assignments. Can you see the Octave now?
Yep.
Yes.
Okay, good. So let's just see if my sketch was anywhere near decent. So I'll go XY equals mesh grid. And I'll go -2 in steps of 0.2 up to 2. -2, and Y will go from -2 in steps of 0.2 up to 2. That will make X and Y big arrays. I don't want to print them out. There'll be the grid of all the X and Y coordinates. I don't want to print it out, so I put a semicolon. And then I do the quiver command. And I have to put the X and Y coordinates of little vectors. And the X coordinates will all be 1s. An array, a big matrix of 1s of the same size as the matrix X. And the Y coordinate will contain the right-hand side of my differential equation. And I have to go X dot to the power 2. Because if I just went X squared and X is a matrix, it would try and do a matrix times a matrix, as in the as we said.
Yeah, I was on that problem.
Want to do that. So you just want to square each element of the matrix X by itself, and that's just X dot. There we go. So that does look a bit similar to what I had before. And now I've got more arrows. So you can imagine the solution going up here, tangent to the arrows, horizontally, and then down, and then horizontally, and then up. And you can kind of see where there's going to be a solution that's just asymptoting towards a straight line there. And then over here, there's going to be ones that go, some solutions going down, solutions going up, and then they're off. And so that already gives quite a good picture of what the solutions are going to look like. And the other question was sketch the solutions. The steady states. Are there any steady states?
Yeah, if you've got these equals 0, that would be a steady state, wouldn't it?
Yeah, so this is that's why I asked that question, because this is a bit subtle. Initially, I did set the right-hand side equal to 0, like when x and y are both 0, dy dx is 0. But that just by itself, that just means the solution is a horizontal tangent at that point. So not for all x. So for a steady state,
Yes.
you have to have the right-hand side being 0 for all x. And this one doesn't have, there's no value of y that makes this function equal to 0 for all x. So the answer is no. There are no steady states for this particular one. And if there were, you would be able to sketch them as horizontal lines. The graph of the steady state solution is just y equals a constant.
Yeah. Is that the autonomous equations? No, it's wrong. We got that wrong.
Yes, so you'll get these steady states when you have an equation of the form dy dx equals a function of y only, which is called an autonomous equation. There's no x's on the right-hand side. Then it's possible wherever f of y has a 0, then you will have steady states. So for example, you have this equation, dy dx equals sine y. Again, nonlinear equation, that's hard to solve. I can get some solutions because sine y is 0 whenever y is an integer multiple of pi. So y equals 0, there's a horizontal solution there, constant solution, y equals pi, y equals 2 pi. Those solutions are easy to get. Okay, so the next topic was separable. They always look like dy dx, at least unless the variables have different names. It's always a function of x times a function of y. And let's do an example. But the catch here is that you may have to do some algebra on the right-hand side to rearrange it to make it look like that. So in particular, if I have dy dx equals x plus xy.
We can't see your screen.
Oh, not again. Wait a minute. I thought I shared the whole. Okay. Oh, screen sharing. Oh, I must have stopped the screen sharing. Don't know what happened there. Okay. So I said separable equations. They will always take the form dy dx as a function of x times a function of y, but it might not always be obvious what the f of x and g of y are. You might have to do some algebra to rearrange that to write it as a product. So I've chosen an example here where you do have to do that, dy dx equals x plus xy. So if you wanted to solve this one as a separable equation, what would you do?
Would you
Factor out x and then
Yes, that's right. So writing things as a product is means factoring. So you have to factor out the x. Now it's a function of x times a function of y. So what would the next line be?
divide both sides by 1 plus y.
Yeah, that's right. So you're going to get dy, sorry about the hokey looking equations, dy divided by 1 plus y to x, and we'll do it all in one step. The dx comes up on the right. Yep. So the separation step where you separate out the variables, get all the x's on one side and all the y's on the other, that's like the crucial step in this method. That's what makes it look So we'll finish this one. What's the now I integrate both sides?
Just quickly, can I ask?
Yeah.
That when you go dy by dx, sometimes it's like they're placeholders, and sometimes they seem to perform a function. Like there, is that just to tell us that they're both derivatives? That there's dy there and dx there?
That is a good question. We do bandy those symbols around a bit in different meanings. To understand this what's happening with the separation of variables, you really got to go back to the full derivation of why it works, which is really coming from the chain rule and the change of variables formula for integrals.
Okay.
So if I didn't do that step, I just moved the y's to the left, I would get integral of 1 over 1 plus y.
Yeah.
dy dx, and then I'm integrating both sides with respect to x. So the clever part of the separation of variables thing is that dy dx times dx can actually turn into a dy.
Oh, so in that case, we're actually treating dy dx like an algebraic entity. So
yeah, well, the proof, yeah, yeah, you can think of it like that. You can think of cancelling the dx's, but the reason that dy dx times dx turns into dy, that comes from the change of variables formula when you do integration by substitution. So that's the missing step here. But once you know that, you don't need to go back and do this intermediate step.
So the change of variables, do you mean like turning let this function equal u? So
yes,
its derivative is du, so on.
Yes.
Yeah.
So suppose I said, here's an integral. I don't want to do this integral with respect to x. I'd like to change variables and integrate with respect to y.
Yeah.
What would the change of variables be? Well, dy, we know it's the derivative of that new function times dx, so, which is exactly what I'm doing then. Changing dy dx times dx into dy. Yep.
Yeah.
Okay. So if we go back a step, this is the other thing that's going to come up this week, is remembering integration and differentiation. So how do I integrate?
That would be ln, wouldn't it? 1 plus y.
Yes, that's right. Natural log of 1 plus y on the left, which you can do that integral either just by knowing that one, as Callum did, or you can do it by a substitution. You could let u equals 1 plus y.
And so since it's just dy, it's not implicit. So it's,
that's right.
If we kept it as but
that's the clever part. At this point, once you've got no x's anymore, you can evaluate. We've changed variables to make y now just, it's sort of like we're making y an independent variable. Just
yeah.
Very good. And what do I get on the right hand side?
Half x squared plus c.
Yeah. X squared plus c. And this one doesn't look so bad, so I will go on and solve 1 plus y equals exponential of square root 2 plus c. And now we'll do this thing, which is, because equations like this come up all the time, I will keep going, because very good idea to simplify this by breaking apart that exponential using the rules for exponentials. And then I'm just going to call e to the c. I'm just going to call that a new constant a. And this happens quite a lot, where I think someone asked about this on Discord, you can change or redefine your constant integration to be something else.
Yeah.
So that is done quite a lot to get a simpler formula. So now I get Well, if this was the absolute value of 1 plus y, that means 1 plus y. Well, it could be plus a e to the x squared or minus a e to the x squared, but I haven't said what a is yet, so it can be any number. So I don't really need the sign. And I've got my solution. Yep. So it's when it works, it's a good method. Now you may get a gnarly function to integrate because you have to move the y part over to the left-hand side. But apart from that, it is a surprisingly powerful method.
So with that constant, you had exponent c. Is a just a stand-in for it? So it is still e to the c. It's just written as a e, or is
Yes.
It does. Okay, cool.
Yes, it's still edited. Yeah. But the once you've redefined it, you would normally just stick with the new one. So like if you were plugging it, substituting an initial value, you would just stick with your new constant.
Yeah.
Yeah. Okay.
So what about you put Aline absolute value of 1 plus y, because 1 plus y can't be negative.
That's because the antiderivative of 1 over y dy is log absolute value y. Now, you don't always worry about that little detail, but if sometimes it's important. That's what it should say in the table of integrals. Yeah.
So
the
all
function,
I have to do in the test, for example, is look at the table of integrals.
Just trying to think of it in my head. Okay, how would I solve this one?
Factor it quadratically.
Yeah.
So it's y. Is it y plus 2, y plus 1?
That one does factor. That's true. So it's an option. Yep.
You'd still need to divide it on both.
Yeah.
To bring it both of them down to the divide by it and bring them down to the left hand side. Oh no, yeah, and then get the y's onto one side and then just have it dx.
Yes, that's correct. So what will I have after I've done that?
So will it be dy divided by that quadratic function equals dx?
That's right.
And you'd have 1 dx on the
Yeah.
right side.
And then you just have dx. That's right. Because when you've divided both sides by that y plus 2, y plus 1, you've just got 1 left on the right hand side. Yeah. So in particular, you're always you're doing operations like factoring and multiplying through by common factors. You're not going to be subtracting things. So for example, just this is an aside here, y dx equals x plus y. That is not actually separable.
Because you can't divide by it.
Yeah. So you could move the y. It's true that you could do this. You could go dy dx minus y equals x. But you haven't actually separated it because you've still got x's and y's together on the left-hand side. So it's not always obvious just by looking at it or by doing a little bit of algebra whether or not it is separable.
Ah, I see. So the y has to be connected into like as in to divide by that like dy dx. That's
that's right.
That's why he that Milo could do that, and it was a Discord thing. Yeah. That
Oh
makes
yeah,
sense.
yeah. You could, yeah. Because sometimes you can do both, can't you, if it's a very simple equation?
Yeah, yeah. dy dx equals y. That one is linear and separable. Yeah.
Yeah.
Or y dy dx equals y plus 1. Yeah, that's linear and separable. Anyway, let's get back to this one. I've chosen a more complicated one because now I have to integrate the left-hand side with respect to y. So I have to remember the technique for doing that kind of integral.
I'm trying to remember it in the head.
Because it could be, could you do it as a partial fraction?
Yeah, exactly. Brilliant. This is a partial fractions one. So what are the main techniques of integration?
That would be a over.
We've got the elementary ones where it's just look it up in the table. We've got substitution, where you set y equals a function, or you set maybe u equals y. Du is h prime of y. Change it all into u's. So that's sort of the chain rule. There's integration by parts. Be used for things like if you had the integral of something like y sine y dy, especially where you've got different functions multiplied together, different types of functions like y and sine y. That's where you use integration by parts, or integral of ln y. That's also done by integration by parts. And then the other partial fraction is for rational functions. And rational functions are one polynomial divided by another function. So that is a good thing to remember. So how we do that? First, you just go away and work out the partial fraction expansion of that function.
Yeah.
But hard to do without being able to write, but it's 1 divided by up to the denominator. So that's going to be something over y plus 2 plus something over y plus 1.
Yeah, that's what. Yeah, okay. I
Yeah.
wasn't sure.
Really putting this, using this technology for its worst possible. Yep, that's good. So it must be a sum of two fractions, something one constant over y plus 2 and another constant over y plus 1. And what's the next
Yeah.
step?
Oh, sorry.
There you go.
You can separate out the constants times y and constant times numbers, and then just equate them. Is that all right?
Yeah, yeah. What you're going to do is you're now going to go backwards. You're going to add up those two fractions and put them over a common denominator.
Yeah.
And the common denominator will always be the one you started with by design. You chose the two factors to be that way. So you're going to get a times y plus 1 plus b times y plus 2 all divided by 1 plus 2.
Yeah.
And now if you look at what I started with and what I've got, the denominators are the same. And I want them to be the same function, so the numerators must be the same as well.
Yeah.
So 1 is equal to a y plus 1 plus b y plus 2. What is that? That is equal to y times a plus b plus a plus 2b.
Yeah.
And the thing is to remember is you're not solving for y, you're solving for a and b to make this the same function of y. So since there are no y's on the left, a plus b must be 0, so that you get no y's on the right.
And then is it a plus 2b equals 1?
Yes.
Got A equals 1 and B equals -1.
So we get A plus B equals 0 and A plus 2B equals 1. So that's, you get 2 equations and 2 unknowns, or if you had a more complicated one, you get like 4 equations and 4 unknowns, and you could solve them for the coefficients. What's the solution? If I subtract them, I get B equals 1.
Cool.
-1 plus 1, -1 plus 2. Yeah, that's good. So I can go back here. A was -1 and B was 1. Once you know the partial fraction expansion, now it's very easy to integrate because you've broken that function apart into much simpler terms, each of which is one of the elementary ones. So the integral is minus ln absolute value y plus 2 plus ln value y plus 1. And back on up here where I was working, and I get integrate the right hand side, you get x plus c. Yeah, so there's the implicit solution. Yeah.
I think Tahu was just asking when you got cut off.
Oh, yeah.
Do we always write? Is it implied that natural log is an absolute value, or do we always write the absolute value?
Well, not everybody always writes absolute value, to be honest.
Okay.
It's one of those things where occasionally it'll be important. Like if y was negative, then you might need the absolute value sign. Yeah.
Okay. Yeah.
Not going to be much wrong. I know that we mathematicians are sticklers for detail, but we have a limit as well. Yeah. So if you look through the textbook, do I have the textbook here? There should be a lot of problems where you get to practice your integration. Oh yeah, there's the table of integrals, differentiation. That's good. Brief table of integrals. Well, that's already not that brief. That's already more than anybody would need. Anything more complicated than that, I'm going to do on a computer anyway. Oh, here it is. See, here it is. Integral of 1 over u du is log absolute value u. So they did write it in there. That's good. Okay. Okie dokie. So if we go to section chapter 2.1, 2.2. No, where's it gone? This is separable. Here we go. Here we go. So these problems will give you as much practice as you want on your integration techniques.
Yeah.
And you notice, look at one like this, 19. It doesn't obviously look separable, does it? It looks like a complete nightmare there. But luckily, they are telling you that this problem is in fact separable. So that means you've just got to work out what to do algebraically to separate it. And what you've got to do there is factor it. And you notice that it's a little bit more complicated than what you might be used to. But if you notice, the first two terms have got a common factor x. So I'd write that as x times y plus 3. And then I notice I've got minus y plus 3. So then I would factor it again, and I'd get x minus 1 times y plus 3. So I would have factored the numerator. I don't think I can, maybe, yeah, I can bring up my typing window. Here we go. Can you see both windows?
Yep.
Yeah.
So for number 19, I'd be factoring the right-hand side. First, I'd write it as x y plus 3 minus y plus 3 on the numerator. And I see both terms have a factor y plus 3, so I get y plus 3, x minus 1. In the numerator, and in the denominator, I see I've got the first two terms have an x, so I get x, y minus 2. And then I see I've got 4y minus 2, or y minus 8. Y minus 2. So both the numerator and the denominator factors into a function of x times a function of y. So you would be able to separate that one. And then some of these other ones here, like, actually, this is a really easy one. This one is much easier than it looks. What would you do with this one? Oops. 24.
Oh, you take the y squared minus 1 and divide by that, and you just get 1 over squared minus 1 and 1 over x squared plus 1, and then dig.
Yeah, that's right. So you've actually got the same function and to integrate twice there. You've got to integrate 1 over x squared minus 1 with respect to x, and you've got to integrate 1 over y squared minus 1 with respect to y, which would have to be done with partial fractions, but it's the same function each time.
Or else you could just go y squared minus 1 times x squared minus 1 to a negative 1.
Yeah, but you're still going to be faced with the same integral to do. So I would do it the first way. Yeah.
Do we have time to have a quick look at the first question from the workshop? I think it was still separable. It was just kind of
I got stuck on the first one, and then I did the rest of them and came back to it. And
yeah,
I actually had erased all of my work and just started again, and then I got through it.
Erased your work? Oh no.
Yeah, I know I did, because I was stuck.
I think a lot of it is just the algebra at the end, just to get it to y on one side and x on the other. That's the difficult.
Okay, cool.
Hang on. There are no, where are the suggested problems?
Down the bottom, workshop.
Oh, the workshop. But there's supposed to be suggested problems too.
They're even further below, aren't they?
Yeah, they're below that.
Below.
Practice problems, you're right. Okay. Is that what you meant here?
Yeah.
Or did you mean the workshop?
Oh, no, sorry, I meant the workshop. Yeah.
Okay.
Also, we can't see the workshop 2 solutions. Is that?
Oh yeah, they're published on Friday.
Oh, right. Okay, cool.
Yeah, yeah.
Will you go over them like last week in the Thursday Zoom we did?
Yeah.
We went over the workshop.
Exactly. Yeah, exactly. That's what we'll do. Okay. Okay. Let's see if I can.
Be able to separate that.
Yes. How am I going to do that? So this is a problem.
You just have the y plus 3 squared over the 4x plus 5 squared. You'd separate the, because you separate the, you could square the top and the bottom.
Yes.
And then that means you could separate it out.
Just like the last problem we did.
Very similar. Yeah.
Yeah, right.
That's right. So what am I going to get for the next line?
1 over y plus 3 squared.
Yep.
dy.
Yep.
And then 1 over 4x plus 5 squared dx.
I see. I don't think I got this at the time, but will we just use partial fractions again?
So that is a good, so yeah, so there's the separation step. Now I have to integrate these guys. Now it is a rational function, but it's not a partial fractions one because it doesn't have multiple different factors on the denominator.
Yeah, I used U substitution for
Yeah,
both
so you,
sides.
you can't actually break this apart into a sum of simpler functions. You need
yeah.
vectors. So to do the left-hand side, you put u equals y plus 3.
Yep.
Yep.
Cool.
Okay.
So you just get, if I get it right, that's minus bracket open y plus 3 to the minus 1 equals 1/4 4x plus 5 close bracket plus c.
Yeah, to the -1 plus c. Yep.
Once you've done the substitution.
Yep. Sounds good.
The
Cool.
bit that was getting me was then, now how do I simplify that to get y on one side? And it's taken me all
You can do that. You can do that.
I've done that. I've managed to do
Oh,
that.
you did it in the end. Yep.
It took me a week of like figuring it out and going, oh, right, yeah.
It's the simple stuff that stuffs me up every time.
Yeah.
Can we go back for a little bit, please?
Sure. What do you want to look at?
For workshop A,
Yes. So have you done the separation of variables step?
it's if this is equal to 4x to 1/4x plus 5 dx, whatever it is.
The integral. Yeah. Well, I'll do the one on the left-hand side, the dy one, because I started on that already. So you make the substitution u equals y plus 3.
You share your screen again.
So du is going to be the derivative of the right-hand side with respect to y. So that's just 1 times dy.
Can you share your screen, please?
Oh, very good. There we
Thank
go.
you.
So we're doing the left-hand side. Make the substitution u equals y plus 3. So du is the derivative of that guy, which is 1 dy. So it turns into, dy just turns into du.
Yeah, right.
And y plus 3 squared just turns into u squared. And to integrate that one, I'd write that as u to the power -2 du. And I can use the power rule. And the power rule is add 1 to the power and divide by the new power.
Okay, good. So when we get, if we get a perfect square form, then we can just go straight to substitution. So it's
Yes.
just when it's difference of squares or another.
It's when you've got different factors on the denominator. Yeah.
Yeah, right. Yep.
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 And altogether, I've got minus. Now I undo my substitution. U is y plus 3, so I get minus 1 over. And it's very similar on the right hand side.